Okay, good morning, everyone. Welcome back. I hope you all enjoyed the eclipse yesterday. Let's talk a little bit about the final project. So hopefully yesterday by 11:59 p.m. you all submitted your idea for your final project and you thought a little bit about how to break this down into 4 baby steps that will get you there. A couple questions that came up inevitably about this process. What happens if you change your mind or you get 2 weeks into your final project and you find out that what you pitched wasn't reasonable? You absolutely can change your mind. Just let us know when you submit a given weekly report. Type into the Brightspace submission, here's what I had planned for this week. Here's what I've changed to for this week for this reason. 2 or 3 sentences should be sufficient. You are not being graded on your ability to predict into the future about what will and won't work in PyBullet. What you are being assessed on is your ability to map out a relatively ambitious project and break it down into pieces, and your ability to keep us in the loop about what's working, what isn't, and so on. Make sense? Okay, use common sense here, we should be fine. Any questions about things so far? Yes?
How do you make the joints like, not like static, but just like make it so that they don't like detach from limbs? Like there's a significant amount of more tension that actually keeps the limbs together?
Okay, that's a good question. So we haven't talked about that. Simulating a joint well can be tricky. So if there's significant torque acting at the joint, it can pull the pieces apart. My first suggestion is there's probably something else going on in your simulation that's creating undue torque. Better to reduce the torque in the system as a whole than try and fiddle with the joints. There are ways you can make the joints stronger, but usually the joints will generally work well as long as there isn't significant torque. What is it that you're doing that's exerting so much force on the joints?
I have been making my robot jumps like only by using revolutionary force.
Okay.
So like when it's been like bending down and bracing to jump, it's like bending its legs into like not into the main body of the robot, but bending it in enough that like the front legs don't like pull in fully with the back legs, so
Okay.
they like separate from the body.
Okay, that sounds like the kind of thing you want to come see us in office hours about. We can have a look and try and diagnose things and give you a suggestion.
Okay.
Okay. Other questions? Yes?
For the milestones, it's only like a text submission.
The milestones are a text submission. If you want to include a link that points us to a PDF or your screenshots or videos, as you've been doing all along, please do so. So a combination of text and pointers to external resources is what we're looking for. Sorry, I should have made that clear up front. Other questions? Yes?
Also, like, what are the other types of like forces that you can use in the joints? I saw that you have like specifically that revolutionary is like the type of
Revolute joints, meaning that they revolve or it's angle. There's the other one, which is a linear joint. We talked about this before. So you can create a piston in PyBullet where you take 2 links and connect them together with a linear joint. And now forces applied by that joint to the 2 links that the joint connects will pull the links towards one another or push them apart. That's a linear joint. Yeah. So remember, when we're dealing with physics engines and robots, there's 2 types of forces that we're talking about. There's rotational force, force that's trying to turn or twist something. That's called torque. So a motorized revolute joint, the motor is applying torque. It's applying rotational force to change the relative angle between links. If you use a piston or a linear joint, the motor at a linear joint is going to apply linear force. It's going to change the relative positions of the links rather than the angles between them. Torque and linear force. Good? And again, it's not immediately obvious how to implement linear joints. Come and see me or the TA and we can help you with that. Other questions? You will notice on the subreddit, there's a pointer to tips and tricks. So there is a whole bunch of these additional things that you can add in. You can change the masses of objects. You can include spheres rather than rectangular solids. There's a bunch of stuff there. If you haven't had a look already, you can browse through there for ideas. Okay. I want to talk a little bit about A and B testing. This can be particularly confusing, especially if your A and B variant of your algorithm, whatever you're proposing, includes different fitness functions. Let's look at an example. Let's assume you've got the parallel hill climber, and because I don't want to write out too much on the board, let's assume a population size of 2. So we've got 2 parents, and we'll just assume whatever the fitness function is, these are the fitness values of the 2 parents. Each parent produces a child. The child is better than or worse than the parent. We replace, and so on. And over time, we should see values doing something like this, right? Gradually increasing from generation to generation. And same thing for the second parent. Okay. I haven't said anything about what the fitness value is, but let's assume that this is version A of your code. Let's think about the up, up, and away project, which is to get your robot to jump. Maybe in fitness variant A here, in variant A, the fitness function is the height of the main body of the quadruped. That's the fitness function you're trying to use to get your robot to jump, and you get this. As some of you may have noticed, sometimes it works, but sometimes evolution perversely instantiates jumping in your robot. In what way? Standing on its tiptoes, right? So you become disillusioned with the fitness function that maximizes height of the main body, and you formulate a new version of your code base, variant B, in which everything is the same, except you change the fitness function to something like maximizing the number of time steps in which all 4 feet are off the ground, which means now your fitness function has become an integer value, the number of time steps for which everything's off the ground. So maybe parent 1 enjoys 4 time steps in which all 4 feet are off the ground, parent 2, 3, and you start to get something that looks like this. Which of these 2 algorithm variants produce better jumping? We can't say because we have 2 different definitions of jumping. So A/B testing is tricky if you're going to use a different fitness function. There are 2 options if you do want to compare 2 different fitness functions. You take something else that isn't in A and B and use that as your measurement for how well evolution is evolving that behavior into your robot. It's a little tricky to see what that is for jumping because we have 2 definitions of jumping. We have to come up with something else. Like what, for example? Jumping seems like kind of a simple, intuitive thing. You jump or you don't, but as we can start to see, there's different ways of actually measuring jumping. What makes for a good jump beyond just these 2 things?
Maximum z-value.
That's the maximum z-value is this. We're already selecting for this. So if we were to say, we're going to look across these 2 versions and see which one produced better positive height of the main body, which of these 2 variants do you think is going to do a better job at that?
The airtime one, because it's being weighted higher than the maximum height.
We're assuming in this case we're not even measuring the height of the main body, just the amount of time that all 4 feet are off the ground. If we want to see the height of the main body, it's going to be algorithm variant A because that's what evolution was selecting for. So we need to pick something else.
Are you asking like what we should change the fitness function to so that it weighs both of them equally?
The way we've set up this experiment here is in general, in this experiment, we're interested in evolving jumping. Which variant of our code, A or B, is going to evolve better jumping for our robot? But we're in a tricky spot now because we've already defined two different ways of jumping, and we're asking which of these two algorithm variants produces better jumping. So it's not fair to say, well, we'll use this definition of jumping and ask which of these two code bases produces that version of jumping, because this variant will produce a better version of that jumping than this. So we kind of need something like C, something that is not here and not here, that most people would agree is a good feature of jumping, that isn't obviously in either of these, and say that C is our version of jumping, and we want to see which of these two produced a better version of that.
Like how far off the other feet?
How far off the ground all 4 feet are, right? That's a pretty good jump definition of a high jump, which is how far are your feet off the ground, the height of your feet. That would be an ideal C, because it's not immediately obvious that either of these are selecting for that. Make sense? It seems like kind of an odd way to go about an experiment, but for our purposes, that's what we're kind of looking for. Yeah? If your A/B testing does not have a difference in the fitness function, then you're okay. So let's imagine, for example, we're still doing the up, up, and away project, but in version A, we're still selecting for the height of the main body, but in algorithm variant A, everything is exactly the same, except the body of the robot. In variant A, we're going to evolve for jumping in the quadruped, and in variant B, we're going to evolve for jumping in the hexapod, in which case we wouldn't have integers, we'd be back to floating point numbers. Okay, which is doing better at jumping? Now it's a little more obvious, right? So for those of you that are doing A/B testing in which the fitness function is the same, but you're changing something else, like the environment of the robot or the body of the robot or the cognitive architecture of the neural controller of the robot or the mutation rate or how mutation is done in the evolutionary algorithm, there's a whole bunch of other things you could change. It's relatively easy to conduct an A/B test, but if you're changing the fitness function between A and B, it's not as obvious. And if you get stuck, come and see the TA or myself and we can talk about it. Make sense? Okay. All right, question.
Just one small question on the
Sure.
final project. Is there like a certain number of children during like each well, I was thinking about possibly like increasing the amount of like evolutionary variation I can get by increasing the number of children that each parent was like comparing itself to find like the strongest evolutionary fitness of each of the variations.
Okay.
And have you applied much like having like multiple children for each parent, and like have you found that there's like a certain number of children that like increases the fitness of the like robot consistently?
That's a great question. So we've been talking about the parallel hill climber, which is a very simple evolutionary algorithm. You could, for example, have each parent produce 3 children or 5 children or 23 children. Does that make a difference? That would be a great A and B test. Maybe you evolve for jumping in the quadruped with the standard parallel hill climber from assignment 9, and algorithm variant B is you increase the number of children that each parent produces, and then you try and answer the question you just asked, which is there a certain number of children, more than one, that over the same amount of evolutionary time produces greater fitness? That would be a great final project.
That's good to know.
Okay. Okay, all right, back to our ongoing discussion about open problems or challenges in the field of evolutionary robotics. We are going to finish this discussion today with the last open question in robotics, which is obviously if we want to make machines, that are useful and safe out here in the real world with all of us, we're going to need to teach them how to be useful and safe. It's not very scalable to have one person teaching or evolving behaviors for a single robot and then trying to cross the gap. How do we construct a greater algorithm that includes people and as many people as possible? As you're going to see in the Twitch Plays Robotics project today, we have some evolving robots and very large numbers of people that are directing that evolutionary process. They are not writing down mathematically fitness functions. They are going to influence the evolutionary progression of the robots using natural language. That's what we can assume most people have in common. And we are all of us humans instinctual teachers, whether you know it or not. It's in there somewhere. And the most intuitive and most comfortable way for us to teach is with natural language. But if we're dealing with robots, robots are embodied creatures and they act. They sense, think, and act. So we need to make a connection somehow between language and action. As we've recently learned, if you want to make non-embodied machines like ChatGPT, it seems like you can get away with just teaching them with language since they don't need to act. But some of us would argue that there's something missing there. Perhaps the way to go is to connect language with action. But human language, English, Mandarin, doesn't matter. It seems very far from the nuts and bolts of physical embodied action in the world. Poetry, language, mathematics, chess, they are abstract, non-touchable things that are very different from learning to walk, right? It feels that way to many of us. But thinking about thinking is misleading. So last time we finished off exploring the fact that there seems to be, or we're learning about the fact that there are many, many connections between, at least with humans, between language and action. If you watched the lecture from last time, you saw some of these interesting brain imaging studies that have been done with the motor strip. This is the part of the brain that would be underneath your headphone strap. When you talk to someone who's lying in a brain scanner and you mention action words, those parts of the brain tend to light up. That was the Pulver-Muller experiment from not that long ago. So this is kind of a recent finding. There is a connection between language. As I'm speaking, if I use body-related words like talk, lick, grasp, pick, I am lighting up parts of your motor strip right now that correspond to grasp, lick, pick, and so on. Yes?
Another interesting one is if you think a word in your head, you can usually feel yourself saying it.
Absolutely. There are many, once you start to think about it, there are many connections between language and action, which is good news for us roboticists. If we're going to start talking to robots, those robots are going to have to make a connection between language and action also. But how? How are they going to make a connection between language and action? We're spending a few minutes now seeing at least how these things are connected in humans, not necessarily how they became connected. Obviously, our ancestors were able to walk and lick and grasp and walk and kick long before language existed. Action was there long before. So somehow language must have got grafted on top of language. Yeah? We ended last time on a cliffhanger with George Lakoff, a very, very famous psychologist and linguist, who pointed out that there's much evidence in language about how, and this is a hypothesis still, how possibly language got started in humans or primates because it was connected with our actions. Lakoff is particularly famous for formulating this idea of embodied metaphors. If you're a non-native English speaker and you start to hear English idioms like don't jump to conclusions or don't look back in anger, Many non-native English speakers can tell you exactly what these idioms mean the first time they hear them without having them explain to them why.
Because they're related to the physical world.
They're related to the physical world, not just the physical world, our relationship to it, right? Don't look back in anger. Our physiology, our primary sensory apparatus, which is our eyes, point forward. We were and arguably still are apex predators. For apex predators, it's very good to be focused on what's ahead. You don't necessarily need to look around you because no one's trying to sneak up on you. You're an apex predator, right? So our primary visual sense is forward. We tend to move in that direction. So if we're moving and we literally look back, what do we see? We see things that are in our recent past. Same thing with looking forward to future events. I see something and it becomes a part of my future experience. There are hundreds, if not thousands, of embodied metaphors in every language group. We're all English speakers in this room, so we're going to play the embodied metaphor game in English. What are some other embodied metaphors? Don't hold back. Try and lean into this. It's not that hard. You don't need to tie yourself in knots. Are you going to make me pull this out of you?
Let your imagination run away.
Don't let your imagination run away or run wild. Cat got your tongue?
Falling behind or something.
Sorry?
Falling behind.
Falling behind. I bet you most of you are thinking about that, right? You're probably falling behind on all your projects and tests this month. Others?
Staying grounded.
Staying grounded. Great.
This one's a bit of a reach, but
A bit of a reach. Well done.
pulling at straws.
Pulling at straws. This one is a combination of physiological and cultural, right? Drawing the short straw, that's a cultural artifact. Many embodied metaphors are a mix. Some of them are purely physiological.
We should get in touch sometime.
We should get in touch sometime. Great. Let's pick up the pace. It gets easier the more you do it. Thinking about thinking is misleading. Language does not necessarily feel like an embodied thing. It feels like a difficult thing to do.
Another one is like something's burdening you.
Something's burning you, yeah.
Burdening.
Burdening you, yes, burdening something, yes, absolutely. I have a burning need to hear more embodied metaphors.
I'm tripped up.
Yeah, exactly. I'm tripped up. I want more. I'm not going to take this lying down. Did you have one?
Sure, yeah.
Ah, okay. You probably had one. It was probably on the tip of your tongue.
I'm trying to think of something that's like you staying in place.
Okay. You're stuck at the moment, right? You're stuck. Okay.
Being rooted to the ground.
Being rooted to the ground, absolutely.
Go with the flow.
Go with the flow.
Swimming upstream.
Swimming upstream, excellent. Some of you may be feeling very behind with all your coursework at the moment. Is that making you depressed? Are you feeling down?
I'm sure I'll
Make-
get ahead.
Sorry?
I'm sure I'll get ahead.
I'm sure you'll get ahead of it. Absolutely. Stay ahead of it. Why is depression associated with a direction? Why is an emotion associated with direction? Looking forward to and looking back, that makes sense. It makes sense why for future time, for most cultures, it's ahead. And for most cultures, the past is behind. Not every culture, actually. There are some exceptions to this. Why emotions? Why is depression a downward thing, not an upward thing?
So this might be me falling into the thinking about thinking trap.
Okay. Falling into a trap. Well done.
But for me, generally, when I feel depressed, I feel weighed down.
You feel weighed down.
But
Okay.
when I am not depressed, I feel lighter. So there's
There's some sort of emotional gravitational force.
It could also be like rooted in like religious thoughts as well, like in the future, maybe we're going to heaven.
It could be. Why is in many cultures, and again, not every culture, the good place up and the bad place down? When you feel depressed, you feel low. When you don't, you feel lifted up. Which came first, heaven or the feeling of a direction associated with emotion? This is not a religious studies class, so we will not answer that here today. Our point here today, the point I'm trying to make or impress upon you, is there seems to be a very deep connection between action and our ability to understand language. We seem to have a common reference frame for grounding language in our physiology, actually how our bodies are made, how we move, and how our relationship with the world changes as we move.
So this is kind of a weird question, but a lot of the things we just were talking about are kind of interoceptive. They're very much rooted in our sense of like, not just where we are in space, but like our organs, if that makes sense.
Absolutely.
Is that something you can put into a robot? Is that some, can you, like, how would you go about trying to do that?
Yeah, okay. So perfect. How would we do this? There seems to be all this evidence of connections between abstract concepts from language, like prospection. Mentally imagining what's about to happen in the future. That feels like a very abstract thing, and yet this abstract building block of intelligence, the ability to think ahead, seems to be connected with our very physiology, the direction in which our eyes point, and the way we feel most comfortable moving about in the world, all the way into things like internal actions, right? Internal organs, right? We were just playing the embodied metaphor game. I wanted you to really put your heart into it, right? How's that going to work for a robot that doesn't actually have a heart? Seems tricky.
If you have like different input neurons that might be like associated with possibly like different actions.
Now we're getting somewhere. Actions are possible. We share that in common with machines. We can instrument machines with sensory systems. So maybe we can train or evolve machines to connect sensation, at least, in terms of sensor values, with language. That's exactly where the Twitch Plays Robotics project is going to start. I want you to imagine a quadrupedal robot. Shouldn't be too difficult for you to imagine. Shouldn't be too much of a stretch for you. Assume this quadrupedal robot has 4 binary touch sensors in the 4 feet, and this robot is running about in its environment, and my little cartoon figure down here is meant to represent how the robot's sensation is changing over time. No evolutionary robotics at the moment, just a robot that's acting in the world, and as it's moving about, it feels pressure on its feet, or it's getting +1s from the touch sensors in its feet. And by chance, at some point, just by chance, maybe it's equipped with a random neural controller, all 4 feet come off the ground, and the robot senses all 4 touch sensors go to -1 at that point in time. And at that point in time, from somewhere, the robot hears JUMP. The robot doesn't know what this is. It's just a random collection of symbols. Recall the Chinese room. No understanding yet. Just 4 strange symbols happen to come into the robot's neural controller at the time at which all 4 feet left the ground. The robot goes back to running around. It doesn't hear this. And then again, by chance, all 4 feet come off the ground. 4 -1s, and suddenly the robot, quote unquote, hears JUMP again. What can the robot start to conclude from this experience as it's repeated over and over and over again?
Just an association between the symbol and the action.
A simple association. From the robot's point of view, this symbol, this symbol, this symbol, and this symbol tend to be associated in time with -1, -1, -1, -1. A simple association. Nothing fancy at this moment. This is known as the symbol grounding problem. Problem meaning if you have a whole bunch of symbols, as we saw before, from a machine like the Chinese room that has no ability to act or do anything in the world, the best thing that this non-embodied machine can do is still learn associations, but it can learn associations between the symbols of language and the other symbols of language, which is exactly what ChatGPT has learned to do, and it does it very, very, very well. We now have an example of something that doesn't solve the symbol grounding problem. These symbols are not grounded in action in any obvious way. For ChatGPT, symbols are just associated in the sense of ChatGPT knows when these symbols of language appear to humans, humans tend to continue on with this set of symbols. ChatGPT can predict the next token in a string of letters or words or sentences. We, and possibly machines, have another way to ground symbols or deal with symbols, which is to ground them in the soil of sensor motor experience. For our cartoon robot here, it's learned an association between a very small piece of language and its own felt experience. So far, so good? Okay. If a robot can do that, imagine this quadruped keeps moving around, and from time to time, as long as it's moving or jumping or these values are changing, it hears the symbols MOVEMENT. It tends to hear these 8 symbols much more often than it hears these 4 symbols. As long as the robot is moving, people are saying, that's movement, that's movement, that's movement, that's movement. The robot might start to learn an association between JUMP and its touch sensor values. It might also start to learn an association between these 8 symbols and its sensor values. And it might start to now learn an association between these 8 symbols and these 4 symbols. That these 4 symbols always occur whenever these 8 symbols occur. But these 8 symbols sometimes occur when these 4 symbols do not occur. There's an asymmetry here from the robot's perspective. People see that? There's types of movement that isn't a jump, but jump is always a type of movement. So the robot is now not grounding this set of symbols directly in its own felt experience. It's grounding these symbols in these slightly more embodied symbols. So like we just saw in the case of embodied metaphors, you can take any given word from any language and you can start to think about how embodied it is. How directly could a machine or an organism discover an association between those symbols and something that it does, or some invariance or some relationship between itself and the environment? Everybody see that? If that's possible, it's possible that you could make this recursive. A slightly more abstract term, or like political movement, is now metaphorically implying action, but not directly implying action. There are certain movements that might actually be part of a political movement, and then socialism is a particular type of political movement. We're getting up here into very, very abstract terms that seem quite a long way from direct felt experience. So, this is still all a theory, kind of makes sense. You can imagine a machine that starts to learn language like jump and movement. Maybe harder to learn these ones up here, because obviously these words are very far from direct felt experience, right? That's your cue. Thinking about thinking is misleading. In this country, for better or for worse, there are two main political parties. It's a democracy of sorts. When you think about these two parties and elections, aside from stress and anxiety, what do you feel? I'm going to leave political opinions out for the moment. When I say feel, I mean literally feel. What does democracy, in a country in which there are multiple political parties that are vying for power, what does it feel like? How close to actual physical experience can we get?
Like your body sort of feels like tense
Tense, why?
because like there's a lot like sort of going on behind a lot more behind the scenes that you need to focus on rather than just like a lot of like intuitive like actions that we're like looking at like every day.
Okay, maybe things behind the scenes. That's another embodied metaphor. Other ideas?
There's like a push and pull.
A push and a pull. You ever play tug of war? Most people, if you put them in the brain scanner and you talk about the two-party system in this country, the anxiety parts of the brain absolutely light up. But the parts of the motor strip that are involved when people are playing tug of war light up. You mentioned tensing up. If you play tug of war and your muscles are relaxed, you're going to lose, right? There is something that involves or engages most muscle groups when you're playing a push and pull type game. So push and pull metaphors, as you can imagine, are ubiquitous. They're everywhere in political discourse. Things like politics seem like an abstract thing far from the physical body. They are not, or at least you can make a case that they are not. So it seems like there's a lot of evidence or a possibility for grounding language, including so-called non-embodied language, in the felt experience of humans. I don't know about machines. We're going to focus, what you're going to see in the Twitch Plays Robotics project in a moment, is machines that are going to start down here. Whether we can get machines to form associations between embodied words and felt experience, and whether they can then exploit that to understand things like the push and pull of multi-party politics, we'll see. Questions? So far, so good? Okay. All right. So this is a project that came out of my lab. It's still running. If you Google Twitch Plays Robotics, you should be able to find it and actually play Twitch Plays Robotics. Twitch Plays Robotics is designed to enable robots to ground symbols in their own felt experiences. It's a pretty complicated experiment, so we're going to break the description of this experiment down into 4 stages. The robot's going to act. The robot's going to observe how the crowd reacts with language to what it did. So our robot is going to have felt experience, and it's going to have symbols from the crowd, and it's going to try and learn associations between its actions and language from the crowd. And we're going to then measure whether the robot successfully learned to ground symbols in action by asking the robot to predict. We're going to give it new words and new actions and see if it can correctly predict the other one. This is a common way to test whether machines have learned something, expose them to general versions of what we think they've learned, and if they can successfully deal with those unseen situations, they've learned. Okay, here we go. All right, let's start with ACT. We have a Twitch channel called Twitch Plays Robotics. Everybody know what Twitch is? Do I need to explain what Twitch is? One of the most popular websites on the planet. People typically go there to watch people play video games and sometimes type into chat to other members of the chat or whoever is playing the video game. So on our channel, we have a video game, which is a physics engine that is evolving robots. People can type into chat, and we are going to capture that chat and store it in a database. So we've got an evolutionary robotics experiment running, we're streaming it live to Twitch, and we're scraping whatever people say back to the robots. Okay. Okay, I'm going to just zoom in here. We're going to talk, there's been many versions of Twitch Plays Robotics over the years. This was the original one, just to give you a sense of what this looked like. Again, I'm sure most of you have seen or used Twitch. We have a live video stream over here, a relatively simple robot. We gave the crowd the following instructions. If you want to command the next robots, just tell them what you want to do in chat. This is where things are starting. So from the average Twitch user's perspective, they're seeing this crazy simulation over here, and we're trying to suggest to the crowd that they can come up with things they might try and teach the robots. At this point in time, 10 Twitch users have voted to try and teach the robot to crawl forward. 7 members of the Twitch community have gotten very tired of this robot, so they're threatening to riot unless we show them a different robot. This is Twitch, a bit of a chaotic place. That's okay. What even is going on here? So close, I don't even know what that means. Okay. At the moment, luckily, the majority is voting for something they want to try and teach the robots next. Crawl forward. From our perspective as the investigators in this experiment, that made us optimistic that this might work. Why? It's a useful instruction. This seems, crawl forward, seems like something that this simple 3-link, 2-joint worm might actually be able to ground in its felt experience. So far, so good? Okay. All right. Okay. At the moment, at this point in time in the experiment, the crowd had voted on so close as the thing to teach the robots next. This was some offhand comment that some Twitch person mentioned. I doubt this is a set of symbols that this robot can probably ground in its felt experience. We'll see. Okay. All right, I'm going to show you a video now of this in action. This is the current version of Twitch Plays Robotics that's running at the moment. I'll direct your attention to the white text at the top of the simulation here. People have voted to teach the robot to be big. Now they're asking the robot to learn how to move. You'll notice that each robot has a little symbol attached to it. This is the white cyan robot over here. This is the blue silver robot over here. Here's the white robot down here, the cyan yellow robot over here. These are the names of the robots. And you'll notice that someone just voted for GP, to be better at whatever it was, the command that they got. So let's follow along what this user is saying. I'm going to back up for a moment. In a moment, they're going to type in RR. Let me back up again. They're going to type in RR in a moment. Here's RR down here. The command is being big. They're saying that RR is bigger than JR back here. So each of these robots is collecting symbols. The robots do not know what MOVING means, but they're learning an association, which is whatever they are, whatever they're feeling, they are more of that thing than the other robot is. So far, so good? Question?
So when you say better, does like one robot know if the other robot is too?
It's a good point. So in this current version of the experiment, they do. We're going to talk about, I just wanted to give you a sense for what the interface kind of looks like. We're going to spend our time talking about results from this experiment, where the only thing the robots know is how well they're doing at grounding SO space CLOSE, they're probably not going to be able to learn any relationship between their sensor values and that command, that set of symbols. But they may be able to if the symbols are CRAWL space and so on. So far, so good? Okay. Okay. So again, I'll just show you what people are typing in at this point. You can see a lot of people typing in crawl forward, crawl forward. So at this particular snapshot in the experiment, it seems we were lucky. Most of the people on the stream at this time seemed to be getting the idea about what we wanted them to do. And they were implicitly reaching consensus on things that they might be able to teach the robot. They don't know how the robots are being taught this. They don't know anything about neural controllers, presumably, just that this is probably more teachable than New Robot or Riot. Question?
So you just showed us two different modes of this experiment.
Yes.
Like this one, they're shouting commands at the robot. The other one, they're voting on which one is doing better as a sort of training process.
Yes.
What's the relationship between these two settings?
Yeah, so in this experiment, which we're going to talk about now, they're voting for what to teach the robot next, and they're voting. I just haven't talked about the voting mechanism yet. You'll notice that at this moment in time, there is the violet robot on the screen. We're telling them that. If they want to teach this violet robot right now, they should type in violet robot, yes, VY. The robot is obeying the command, so close. So close is the current set of symbols that the robot hears. They should type in VN, meaning no, the violet robot is not obeying the command, so close. That's the voting mechanism. So the robot is getting these symbols, and it's also hearing about whether or not the crowd thinks it's doing the right thing. For those of you that are familiar with reinforcement learning, one of the most popular topics in reinforcement learning at the moment is reinforcement learning with human feedback. This is a version of RLHF. The robots at this point have absolutely no idea what crawl means or so close means or jump means, but they might be able to start to form an association between symbols and what they feel if they hear something and they generate a particular type of sensation, like they actually crawl forward, and they get 1/3 piece, which is yes. The robot hears jump, and the robot doesn't jump. They hear N. The robot hears jump and jumps. The robot hears yes. The voting is the robot's ability to complete this association task. It needs to know if the sensations it's currently generating by acting, it's an embodied agent, it moves and generates sensory information, is the sensory information that it's generating what people would consider an instantiation of those symbols, an instantiation of crawl forward. Everybody see that? So in the Twitch Plays Robotics project, we're going to look at these 3 different types of data. The sensation generated by the robot, the symbols that make up the human-generated commands, and reinforcement, yes or no. Does that sensation align with that action? Okay, so a little bit more about this user interface. You'll notice at this moment in time, we've got the violet robot down here. You can see someone's typed in BN. So there was a blue robot just before this violet robot, and this particular user is saying BN did not obey the current command. That person repeats it again here. So people are voting yes or no, whether the robot's actions or sensations are matching the symbol. Okay, that's quite a bit of detail about experimental design. I'll just pause for a moment. Any questions about that? So far, so good? Okay. Okay. Okay, so let's look at, let's talk about the data set itself. So we've got this thing running and we're generating thousands, and over a few years we generated millions of robots and neural controllers through Twitch, but we used just 2 robot body plans, 2 different robots. The simple 3-link worm that you just saw, and I'm gonna just jump ahead a little bit, this quadruped. So we looked at 2 different bodies. This was actually one big A/B test. And in the Twitch Plays Robotics project, the question we were asking is not just, can robots ground action in language, but do some bodies make it easier for the robot to ground language in action? So robot A, the simple worm, robot B, the quadruped. So far, so good? Okay, let's go back to the data set here. Okay, so R sub 0, R0 is the worm, R sub 1 is the quadruped. For each robot, that robot was shown to the crowd over and over and over and over again, and that tended to elicit from the crowd a whole bunch of C's. These are the commands that the crowd thought the robot might be able to teach the robot to obey that command. So some commands were jump, some commands were crawl forward, some commands were new robot or riot. What other commands do you think the typical Twitch user generated for a robot? I'll give you a hint. This was at the beginning when Twitch was just getting going, and there were no verbal filters on Twitch at this time. I thought I knew every bad word in the English language. I was sorely mistaken. You'd be amazed. When you have a friend who comes to visit whose native tongue is not English, what are the first 6 or 8 words you teach them? You can probably guess. Same thing here. These robots know way more about swear words than you or I ever will.
Hard to ground that.
Is it? Is it hard to ground bad words? We are not going to enter into that discussion here. That's a black hole we'll never escape from. More embodied metaphors for you. Okay, other than those swear words, what else do you think they tried to teach the robots? Those were the most popular, as you can probably imagine.
Basically, so the crawl forward thing.
Crawl forward. So among all the landmines of natural language, there were a lot of terms that, again, gave us confidence that maybe this experiment could actually work. Generally speaking, the crowd tended to converge on embodied words, things that these robots, from our perspective as investigators, we thought, yeah, there's maybe a chance. Some other fun ones were prove Fermat's last theorem. Our robots have not yet figured that one out. One of my other favorites was be yourself. Is this, let's assume this robot is hearing BE space, blah, 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 right now. Would you vote yes or no? Right hand if you think this robot is being itself. Left hand if you think this robot is not. Let's see if we have consensus. Okay, most people feel this robot is being itself. So actually, maybe that is a groundable word. Yeah? It's not up to us, it's up to the consensus of the crowd. Okay. Okay, so again, we're going to start to use this notation a bit as we go forward. Whenever you see R with a single subscript, that references the worm or the quadruped. Whenever you see a C with 2 subscripts, IJ, whenever you see a subscript CIJ, the first subscript denotes that command was sent to that robot. So this command CIJ was issued to robot I, so I can be either 0 or 1. Maybe when people saw the worm, they tended to issue commands like crawl, and when they saw the quadruped, R sub 1, they issued commands like jump, or maybe not, right? The second subscript is going to index different commands. Swear word 1, swear word 2, swear word 3, jump, stay, be yourself, prove Fermat's last theorem. However many commands we got, they got their own ID number, and we had those unique commands. So far, so good? Question?
Are these like reward values at different time steps?
Good question. Are these reward values? No reward yet. We're just talking about the robot's morphology and the string of symbols that they heard. That's it. We haven't got to reward yet. We'll get to reward in a moment.
Did you do any filtering on the commands from people?
No filtering.
So literally
Everything was allowed, for better, for worse. This was a very interesting experiment in many ways. As human investigators, we wanted to try and introduce as little bias as we could about whether or not these robots could ground crowd-generated language. Okay. The next piece of nomenclature here is N with 3 subscripts. In the original Twitch Plays Robotics, which we're talking about today, there was no evolution during the stream. All we did was send one random neural controller, N for neural controller, to the robot, one after the other. So random sets of synaptic weights, that's all the robot was doing. One random neural controller after another. We've got 3 subscripts here. The first one is I. So this random controller was sent to either the worm or the quadruped. The second subscript, J, says this controller was sent to robot I when it was hearing the jth command. So if, let's say, I equals 0, that means this random neural controller is running on the worm. Perhaps this random neural controller is running on the worm while the worm hears JUMP, that particular command. And the kth subscript is just that neural controller. We might have, over the span of this experiment, and we probably did, send more than one random neural controller to the worm while the crowd was trying to teach it to jump. So there might have been multiple neural controllers generating sensor data while the worm was being taught to jump. So far, so good? So we've got two robots, hundreds of commands that the crowd issued to the robot, and thousands and thousands and thousands of random neural controllers that were run on the robots. So far, so good? Okay. You asked about reinforcement or reward. Last piece of nomenclature here, deep breath. We've got 4 subscripts here. S for reinforcement signals. We already used the R up here. So what does a reinforcement signal mean? If I showed you the worm, and the worm happened to be doing this, and the crowd had issued the command JUMP, what would you type in? Y or N? The robot's doing this. We've issued jump. Right hand for yes, left hand for no. Is the robot obeying the command jump? I see unanimous hands going up. I see 9 right hands going up. So SIJK1 would be set equal to 9. 9 members of the crowd at that moment said yes, the robot is obeying the command jump. I did not see a single left hand. Nobody said, no, the robot is not obeying the... Did you have your left hand up? Oh, no, okay. So S sub 0 here is set to 1 for the kth controller that was running on the worm that caused the worm to do this, while J is set to jump on the worm robot. So the kth controller extracted from the crowd a value of 9 for the positive reinforcement signal and a value of 1 for the negative reinforcement signal. The 2 S's are integers. Number of yes votes, number of no votes. So far, so good? Question?
So when you say you sent one at a time, but then you're putting multiple neural controllers, is that like after the simulation ends?
Nope, the simulation never ends. It's actually been running more or less continuously for 9 years now. We're just running neural controllers one after the other on these robots. And as we do, we're computing these values. We're pulling off a data set as we go. So this is quite different from what we've seen in this course so far. That's why this is drawn as a continuous loop. It just keeps going, and the database just keeps filling up with this data, R's and C's and N's and S's. We haven't done anything with this data yet. This is just the observe part. The robot is observing, or we are observing, what we're getting back from the crowd. So far, so good? Okay, all right. So now that we're armed with this data set, let's actually end by looking at what we actually got. So we've written a number of papers based on this continuously running experiment. This is the first bunch of data that we scraped off this experiment that we're talking about today. It took place over a few weeks, and we had 424 different humans. There weren't many bots on Twitch at this point. There were a few, so somewhere in here, there's probably some bots, but mostly humans. Robot evaluations. So we did 57,000 evaluations in about 2 weeks, where an evaluation is running one simulation with one random neural controller. So we executed 57,000 random controllers on the worm and the quadruped over these 2 weeks. We noticed that for 6,388, there was at least one observer on the stream at that time. Again, it's hard to say whether it was a bot or a human being. At this time, they were mostly humans. So about a little over 6,000 of the controllers were actually seen by humans. We got 16,000 pieces of chat back from the crowd during this 2-week period. Okay. Among the 16,000, 8,900 of those pieces of chat were commands. These were things that were not BY, BN, VY, VN. We had a very specific way to tell whether a piece of chat was a positive or negative reinforcement, S0 or S1. Everything else was considered a candidate command, even if it was a swear word, even if it was someone on chat saying, "What the heck is this thing?" We saw a lot of people talking to one another. "Do you know what we're supposed to be doing?" "Okay, thanks for explaining. I get it." Off we go. We just threw it all in a bin, and we assumed this was valid commands. We didn't want to go in and try and pick out what we thought were actual commands. Of the 424 subjects that actually typed something into chat, each person typed in, on average, 21 pieces of chat. If you've ever watched a Twitch stream, you'll know that there were a few subjects in here who did all the talking, and the vast majority of these 424 people said one thing and then left again. That's fine. We saw that among all the 8,900 pieces of chat, there were 266 unique strings. So most of this was repetitions, people typing in the same thing. I've filtered out all the swear words here for you. The next most popular thing was JUMP, which was typed in 385 times by different members of this cohort. So this jump that I chose to illustrate the concept of symbol grounding was not arbitrary. This was the number one thing that folks thought they could get the robot to ground in action, other than swear words. Second most popular thing was walk forward. Third most popular thing was move forward. Fourth was run. Fifth most popular thing typed in by chat was crawl forward. There are many anecdotes from the TPR experiment. I'll share just one more with you. When this started going, we were obviously watching the chat. We saw a lot of chatter among the people chatting on the stream. At one point, somebody said, oh, there's a bunch of scientists trying to teach this robot language. Let's teach it swear words, but I have a plan for how to get this robot to actually learn swear words. So we're going to assume that these investigators aren't here at night. So come back to the stream at 3 a.m. Eastern time, and let's make a plan for how to teach these robots how to understand bad words. What do you think the grad student and I did after seeing that piece of chat? You can imagine we were there at 3 a.m. A bunch of people did show up on the stream at 3 a.m. and they decided on the 4 swear words that they wanted to teach the robot. And they said, whenever the robot moves forward, and this is the swear word, type Y. If the robot moves forward and it's any of the other 3 swear words, type N. Brilliant. If the robot moves backwards and it's the second swear word that's the robot currently hears, give it a Y. If the robot moves backwards and it's any of the other 3 swear words, give it a no. I don't know who this person was, but they clearly had figured out what we were trying to do. I grilled all my grad students, at least it wasn't any of my grad students that I could tell. So they had a systematic way to figure out how to teach this robot bad words. So we didn't know whether to be depressed or optimistic at this point, right? Bad news, they're trying to teach our robot swear words, but good news in the sense that they understood what we were trying to do. And they actually had a pretty good systematic plan for how to get the robot to ground those words in action, probably not the words we wanted it to ground in action. But seemed like it was possible. We thought that was the end of the story. Turns out that there were the good folks who also came to the 3 a.m. meeting. They sent out a message later saying, good guys, they used some gendered language, good guys, come to the stream at 11 p.m. and I've got a plan for how to counteract the bad guys. What do you think the grad student and I did? We showed up at 11 p.m. The good guys, I'm going to use that in scare quotes, came up with the following plan. Actually, what do you think the plan was? By definition, the good guys are always trying to foil the bad guys. The bad guys are trying to ground swear words well.
They just replied with the opposite Y or N.
Absolutely.
The bad guys.
That's it. They created a spreadsheet and they said, here's the user handles we saw for everyone that was at the 3 a.m. meeting. Let's consider these guys the bad guys. Whenever you see them on the stream, whenever they type in Y, type in N. Whenever they type in N, type in Y. At this point, I reached out to one of my social psychology colleagues on campus because I was completely over my head. There were more interesting social dynamics going on in this experiment than I could understand from my professional point of view. Okay. An interesting anecdote, but irrelevant to our discussion today. We're going to focus on just jump in a moment. Yes?
Did it work? Were they able to teach the robot swear words?
I don't know. I don't think there was actually enough reinforcement either way. It's a great question. We ended up getting more total reinforcement for these things. And actually, maybe that might have been because of the good guys. It's hard to say. I don't think we ever went back and actually systematically looked. But my feeling was the good guys poisoned the data set enough that the robots probably wouldn't have been able to ground those words. But we never actually tested that. Good question. Okay, back to JUMP. We took JUMP and we focused on this one. Could the robots learn an association between JUMP and the very large numbers of Ys and Ns we collected from TPR during JUMP? Okay. Couple other things to note. We got a large number of yeses and nos. We got a total of 7,500 Ys and Ns. I don't know whether that was, I didn't know at the time whether that was a big enough number. We wouldn't be talking about this experiment if it wasn't. It is a big enough number for these robots to learn an association between these words and their actions, which we're going to see in a moment. let's see, of the evaluations, all of these random controllers that people saw, a little more than one of them received a yes or a no. So what does that mean? That means most of the neural controllers got 0 yeses or nos. Either people didn't feel like chatting or they couldn't decide. If the worm is going like this but staying in place, is this crawling? I don't know, maybe yes, maybe no, maybe you hesitate from making a vote at all. It's exhibiting the crawling motion, but it's not actually crawling. So maybe yes, maybe no. Some controllers got back 2 Ys and 0 Ns, or 2 Ns and 0 Ys, or 1 Y and 1 N. Some other controllers that just happened to be run on the robot when there were a lot of people on the stream got 17 yeses and 3 nos, or 27 nos and 3 yeses, or problematically, 15 yeses and 15 nos. That's what the data distribution tended to look like. The average human subject typed in about 18 yeses or nos throughout this 2-week period. Proportion of positive reinforcement. This O, as you're going to see in a moment, is a number that ranges between -1 and +1 for a single controller. A value of O equals +1 means unanimous yeses. That controller got 3 yeses and 0 nos, or 33 yeses and 0 nos. An O of -1 means that controller got 1 N and 0 yeses, or 271 N's and 0 yeses. A controller that got 17 yeses and 17 nos would have an O of 0. So what does an average O of 0.28 tell you about the crowd? Got more yeses than nos. Kind of interesting. I don't know whether that's a good thing for us or not. Okay. We've got 2 minutes left, so let's just start to talk about the learn part. Jump was the most common command we heard. So what we did in this part of the experiment is we took all of the N's that were run on the robot whenever the crowd issued jump. So we've got this very large data set that I just walked you through. We're taking a subset from that data set. We're pulling out just the subset of controllers that ran on the robot when the robot heard JUMP. And then we further filtered out those controllers to controllers that were running on the robot when the robot heard JUMP, and we got back at least one reinforcement signal. S sub 0 here, I'm sorry about the font here, S sub 0 plus S sub 1, the absolutes added up to more than 1. We got at least 1 yes or 1 no for that controller running on the robot when it heard JUMP. So we've got the actions of the robot, we've got the symbols that it heard, we've got action, we've got language, and we've got S. We've got the reinforcement signals that we hope are going to allow the robot to learn an association between what it felt, literally what it felt, and JUMP. We'll leave things there for today. You have a quiz due tonight. You're working on your second weekly report. See you all on Thursday.